Hi, welcome to the lecture on standard methods for measuring RVs and their uncertainties. My name is Sharon Wang, and I'm currently a postdoc at Carnegie Observatories. I'm moving to Tsinghua University as a starting assistant professor this fall. We'll start with talking about what we are exactly measuring when we measure RVs. And then I'll talk about the standard methods for measuring RVs from observed spectra. And by standard methods, I mean really the most commonly adopted methods to extract radio velocities from observed spectra. Those are the most commonly used method and sort of the industrial standards these days. And we'll spend most of the time to talk about the origins and mitigation of the measurement errors that are mostly related to the process of extracting radio velocities. Not a comprehensive radio velocity error budget, but just focusing on the part where we're measuring the RVs. And finally, I'll briefly touch on some of the new and non-standard methods for measuring RVs and the future perspectives. All right, so what are we doing when we measure RVs? This is a quick schematic. We go to the observatory, we take a spectrum through our spectrograph at time t equals t0, the first epoch, and we get one observed spectra in the dashed line. And we repeat this measurement at a different epoch at t equals te and obtain another spectrum in the solid line. And we measure the relative Doppler shift between these two spectra. That is Z over here. And I want to emphasize that Doppler shift is not a constant shift in wavelength space, although those two spectra may look like they are a constant shift, but it's actually a stretch. This is really important for constructing a pipeline extracting the Doppler shift. Okay, so what do we need and what do we actually measure? We take spectra at different epochs, as I mentioned, through our spectrograph, and we extract those spectra into one-dimensional data. Those are done through the raw extraction process, and then we calibrate the wavelength for these spectra. And then we perform what we call a barycentric correction. That is, we shift the wavelengths of the observed spectra into the solar system's barycentric rest frame so that we're not affected by the Earth's motion. And we're just measuring the relative changes in the radio velocities of the star. And finally, we measure the Doppler shift between each spectrum with respect to some reference spectrum. Now we're measuring the relative change in the stellar radio velocities. And for this talk, we're going to focus on the final step, just the extraction of radio velocities. We assume that we've done perfectly for the previous 3 steps, but for more details in these steps, which is basically for considering a comprehensive radio velocity error budget, please see Sam Halverson talk and also see Arthur Roy's talk in 2018 Sagan summer workshop. All right, so now let's dive into the standard methods for measuring our radio velocities. There are roughly 2 categories of methods. First being the famous cross-correlation function, or CCF method. This is a method commonly used for stabilized spectrographs, where the spectrograph broadening function or instrumental profiles are thought to be kept unchanged, and you can calibrate the wavelengths of all spectra at all epochs relatively easily and precisely and accurately. And this is also very commonly used for getting less precise radio velocities because it's a method that's relatively easy to implement. So for example, in the extragalactic world, to get some radio velocity of some certain emission lines, or measuring the radio velocity of some distant stars in medium resolution spectra to determine membership of star clusters. And the second method is what we call the forward modeling method, which was first employed to deal with the complicated data taken through absorption cells to obtain precise radio velocities. So the absorption cells will imprint a lot of absorption lines onto your stellar spectrum, which provide your wavelengths and instrumental calibration. But the data are very hard to process, and the extraction of radio velocity is basically only possible through forward modeling. But nowadays, it's more and more commonly used to measure radio velocities for stabilized spectral graphs as well. So first, what is CCF? How does it work? This is a schematic made by Abdra Roy. First, you have your observed spectrum in dashed line. What you do is you cross-correlate your observed spectrum with a mask, for example, or maybe a template. But for example, we're going to use a mask. This is a binary mask with lots of delta functions. Each of the delta function represents a spectral line, and they have different depths at different wavelengths. And you Doppler shift your mask at a certain velocity, say v equals v1, which is at the moment smaller than the velocity of the star, or redward of the speed of the star. And you obtain 1 point in your cross correlation function over here. So this is one value, right? And then you Doppler shift the mask yet again. This time, say you hit the correct answer at the speed of the star, and then you get a minimum in your cross correlation function, and you continue to shift your mask. You construct this cross correlation function, which is a function versus the radio velocity. Next, once you have this CCF shape, you fit a Gaussian to find the radio velocity, which is the fitted peak. And you get some bonus, which is your measurements for the stellar activity indicators, which gauge how active the star is at the moment, which might interfere with your ability to precisely measure the radio velocity component caused by just the pure Doppler shift of the star induced by the planet. This includes the full width half maximum of the line, and also the CCF bisector, which is measuring how the line center changes as a function of depths. All right, so this is really convenient. I just want to mention quickly that the reason why we're fitting a Gaussian is because we were cross-correlating the spectral lines with the delta function, right? And the assumption is that spectral lines are roughly Gaussian shaped. And then mathematically, this is equivalent to you're cross-correlating Gaussian spectral lines with the Gaussian shape and just find the peak of any shape. All right, so where do you get a mask? There are several flavors of masks. The most commonly used ones are customized binary masks. So you use some algorithm to tease out spectral lines and their depths. And you also sort of hand curate your spectral lines and adjust their depths. Or you can change the shape of the mask to non-binary, so maybe a cosine shaped or other shaped mask instead of the delta function shaped. And if you want to go one step further, you can even use a full stellar spectrum, or what we commonly call a template, right? So now you're correlating a spectrum with a spectrum. This is pretty much stepping into forward modeling. So, okay, what is forward modeling? I want to start by telling this example of how we use forward modeling to process iodine calibrated data. This is where we put the starlight, which is in black, the stellar spectrum, broadened by our spectrograph. We put the starlight through an iodine absorption cell, which imprints those green, sharp absorption lines all over the place, again, unbroadened by the spectrograph. And once they're broadened and tangled together, you obtain the observed spectrum in those black dots. And our goal is to model those black dots with a presumably perfectly known model of the stellar spectra and also the iodine spectrum. And the process is called the forward modeling for the following reason. Because the process for constructing a model for the observed spectrum is sort of going forward in time as the spectrum hit our spectrograph, the iodine cell, and then the spectrograph, right? So what you do is you grab your reference spectra, your iodine model, iodine atlas, and your stellar template, which could be some spectrum you derived based on observation taken at one time. You multiply the two, which mimics the process of stellar light going through the iodine cell, and then you convolve it with the line spread function. I should say that before you multiply the two, you shift your stellar template according to your Doppler shift model, right? And then convolve with the line spread function to construct the observed spectrum. So your model parameters include some description of your line spread function, the wavelength solution, which can be coined by the iodine lines, and also your Doppler shift, right? So you're optimizing this whole model to fit observed and arrived at your best fit. So in the context of stabilized spectrograph, forward modeling is much simpler because now all that changed ideally is just the Doppler shift of your stellar spectrum. So you don't need all those complicated modeling components. All you need is a stellar template in the dashed line, say, and then your observed spectrum. And you just try to match the two by feeding a Doppler shift, right? This is very similar to cross correlation, where cross correlation just steps through the parameter space of Doppler shift. But this in forward modeling, you just apply some optimizer, say least chi-square feeding, and you find your chi-square minimum. So you need a stellar template to do forward modeling, obviously. So where do you get the stellar template? This is very tricky. Stellar templates are typically empirically derived, and there are several families of methods that provide you with a stellar template. The first one that's employed for the iodine method is deconvolution, because for the iodine method, you have to use the unbroadened spectra as the starting point of your modeling, and later convolve that with the spectrograph line spread function to mimic the broadening of spectral lines by your spectrograph. So you have to deconvolve some observed spectra. You can tell that this is a fairly challenging and uncertain procedure. And for stabilized spectrographs, since we can assume that the line spread function never changes, we don't have to model this broadening process. So we can just shift a whole bunch of observed spectrum of the same star to the stellar rest frame and stack them together to obtain a high fidelity stellar template, right? And use that to measure the velocity at each epoch. And if you can even go one step further, which is being employed by the Express team. You can stack the spectra, and even morph some other high fidelity spectra to match your observed one to sort of boost its fidelity or signal noise. This is an illustration where they used NSO Solar Atlas, which is in the dashed line, and morph that or stretch that to match their observed spectrum in black to obtain a stellar template in the solid orange line. All right, so those are the basic procedures for the standard methods to measure radio velocities. What can go wrong, right? All right, so But before we go on, I just want to present an interesting fact. This is also a good point where you can stand up and stretch and even distract yourself a little bit so you don't completely drift off in front of the screen. Okay, fun fact number 1. So we talked about measuring the velocities. We talked about measuring the velocities with respect to some reference spectrum. So if you put the wavelengths of your reference spectrum to be at the barycentric rest frame, then we would be measuring the absolute radial velocity of the star for each epoch with respect to the solar system, right? How precise do you think we could measure this absolute radial velocity of a star? I have 4 answers. Maybe we can measure it as precise as our relative radial velocity measurement. After all, the uncertainty reported from our radial velocity code can reach below a meter per second for any single epoch. Or maybe it's not that good, it's only a little below 10 meters per second, or barely below 100 meters per second, or 1,000 meters per second. What do you think? The answer is 100 meters per second also. It is not smaller than a meter per second like we imagined. This is because for absolute radial velocity, we should not be delusioned by the reported error bar, because how good this absolute radial velocity is eventually depends on how good our wavelength calibration is on our reference spectrum. That is, if you have a spectral line and you think this spectral line is at certain wavelengths, that's how you calibrated it. But the precision of this wavelength calibration is only as good as our knowledge of the fundamental physics. That's from line creation, quantum mechanics. What is the true wavelength of this line? That calibration is very challenging, and we struggle at the 100 meters per second level. Okay, so when you talk about absolute RV of a star, or systemic RV of a star, it's almost never as good as well below 100 meters per second, even on our own sun, for this reason. Okay, now let's go back to what can go wrong. What are the origins and mitigation methods for those measurement errors that go into the process I just introduced? All right, first let's step back and think about where errors could arise fundamentally. Imagine if you have perfectly measured spectra with infinite signal-noise ratio, infinite resolution, and your stellar spectrum is identical every time you measure it, except for a Doppler shift. Right? Then, in principle, you can measure the radial velocities perfectly, right? There will be no errors in principle. But if there is any deviation from this assumption, especially that you take one spectrum at one epoch and you come back and measure it again, and its shape changes. So any change in the observed stellar spectrum that is not caused by the Doppler shift, that's not this net shift, that's due to planets, those could induce errors. And we're trying to measure the radial velocity of the black spectrum with respect to the dashed spectrum. You will not get the true answer because of this bias. So there are roughly 4 categories of sources for those errors. So of course, there is the photon counting error. So we don't have infinite signal-noise ratio spectra ever. So every time you come back and measure the same stellar spectra, it'll look a little different just from photon counting error. In addition, when you are making the measurement, maybe you're using a mask or a stellar template that is not completely correct, right? Those could induce errors, you can imagine. And thirdly, if you have some sort of spectral contamination in your stellar spectra that does not shift with the planet and that is time variant, it's not time invariant, then you're making trouble. And lastly, but probably the most challenging problem we're facing in the radiosity world right now is stellar variation, the intrinsic variation caused by the stars. There are lots of stellar phenomena that could cause line shape change or Doppler change in certain lines that could interfere with our measurement of the true Doppler shift of the star caused by planets. Okay, we're gonna talk about them roughly one by one. But first, let's establish some ground truths, per se. When all things are equal, under idealized situations, CCF performs as well as forward modeling. Both methods could reach photon-limited precision. Okay, there is no fundamental limitations per se in, say, algorithmic parts of those two standard methods. When you have the same photon noise, you're using the same stellar template, you're eliminating perfectly well all the contamination. There is no intrinsic stellar variation. And also you're properly and reliably doing the continuum normalization, then you're gonna get the same answer, same correct photon limited radiosity using any of those two methods when you apply those two algorithms properly. Before we move on, I just want to add one word regarding continuum normalization, which is becoming more and more of an issue these days since we're sort of hammering down the other components in the radiosity budget. So if you cannot do a consistent and reliable continuum normalization every time you extract your spectrum, then this is a time variant component in the spectrum, right? When I show all the illustrations, we see a flat continuum with some absorption lines, but when you observe them on your CCD, there is Blaze function, there is varying atmospheric absorption that could change the shape of the continuum, right? We're not gonna dive into details of this topic today, but this is something that's definitely worth looking into and absolutely need caution when you're extracting RVs. But this could be, in principle, taken care of, or at least largely, in the raw reduction process. All right, let's continue. So we've basically checked off photon error. So both standard methods could reach photon limited precision if all the three other components can be taken care of. So let's look at them. First, error in the mask or template. For example, back to this CCF picture, for example, if you have a missing line, say in your mask, say this is missing, and then when you are or you have a wrong shape, say you have like a wrong depth for this line or something, when you're performing the CCF, you're gonna get a biased CCF shape. But the good thing about it is that as long as your observed spectrum does not change over time, the only thing that changes is the Doppler shift, you're gonna get a constant bias in your CCF, which translates to just a constant RV offset, right? Now we don't care about RV offset because it's a constant value as we can measure relative radiosities precisely. That's okay. But the trouble comes when your observed spectrum changes with time and your defects in your stellar templates interact with those changing components of your observed spectrum, then the bias you're inducing in the CCF shape now becomes time variant. And you're no longer translating this error into a constant RV offset, but a changing bias as a function of time. So the error in mask template only matters when you cannot contain the next two time variant component well. Okay, so we're going to focus on contamination and stellar variation. All right, what are the sources for spectral contamination? There are roughly three. Solar contamination. Well, you might wonder, why do you have solar contamination when you observe a star at night, right? You have this thing called the moon, which reflects sunlight. And you also have telluric emission, skylines, also telluric absorption. So if you think of ways of getting rid of these contamination completely from sort of the root of the problem, they each has their unique root solution. For solar contamination, you can avoid the moon when you do the observation, although for doing this type of work, we normally get assigned bright time instead of dark time at our observatory. So this is kind of hard. And you also can mitigate this with a sky fiber. So if you just take a sky calibration spectrum, this could be mitigated, which I'll talk about in a minute. And then there is also telluric emission, which you can solve by just going to a very dark site where you don't see sky emission lines from the city. But there are also other intrinsic telluric emission lines to the Earth's atmosphere you can't really get rid of by going to a dark site, right? You can also calibrate telluric emission by having a sky fiber and just subtract it off from your observed spectrum. But for telluric absorption, which is really tricky, well, this is actually similar to telluric emission. You have to go to space, just get rid of the Earth's atmosphere completely, which is not the desirable answer. So we have to deal with those problems in the pipeline. Let's talk about them one by one. So to mitigate the problem of solar contamination, Roy et al., in a paper published earlier this year, proposed several methods. And this is one of them, using a sky fiber. So what is your problem? Your problem is in your observed spectrum, which is in gray here, you're contaminated with a solar spectrum, which is in blue, which means your CCF, which should be in this more skinny gray, now becomes its fat gray because now it has a new component that's in blue, right? This blue component, you can estimate this component by doing a CCF between your mask, say a solar spectrum mask, with the spectrum you took from the sky fiber. And then your sign spectrum, which is a combination of your target plus the sky, will give you this purple CCF, which is biased. And you just simply subtract the sky CCF from your total CCF, and then you have your target CCF, right? This is a way of eliminating the bias by using a sky fiber. So how well does it work? This is how good it is based on synthetic data, so simulation, and no photon errors are involved in here, just the errors induced by solar contamination. This is before, how much error you have before you remove the solar contamination. This is after. So each plot is a color-coded plot of radio velocity errors as a function of stellar visual magnitude and the sky brightness. As you can see, before you remove the solar contamination, you're subject to substantial errors up to like a meter per second for some fairly bright stars under okay sky conditions, right? This is pretty bad. But after applying the method I just described, you can contain the problem to pretty much a few centimeters per second. So this is 1 centimeter per second. So this really works as long as you have a sky fiber. So this is great. But the assumption here is that, looking back, the way you get the CCF is that you have a good solar model, right? You know that the spectrum in your contamination is a solar spectrum. That helps a lot. And for telluric emission, unfortunately, very often good models don't exist. Traditionally, when we take slit spectrum, so not through a fiber, but through a slit, you can have a very tall slit, and you can subtract off the sky emission this way, because outside the PSF of your star, you're taking a spectrum of the sky, right? But this is no longer available, and it's going to be challenging to eliminate sky emission contamination in the same fashion as the solar contamination. This is still very much ongoing work. All right, so but at least telluric emissions are more or less localized. They're not everywhere in your spectrum like the telluric absorption. Telluric absorption is really obvious, all the way from optical to the near infrared. In the optical, you have microtellurics. In the near infrared, they're just everywhere. So Colin Blake is going to talk more about telluric contamination and how we battle with them in his talk. But here I just quickly touch on it. So the way telluric absorption enters the problem is this. You have your star, and your star going through the atmosphere with those telluric absorption lines. And this is basically mathematically equivalent of you multiply those two spectra together, and those this spectrum goes through your spectral graph, gets broadened, and now you're contaminated when you're trying to do, say, cross correlation with your stellar spectrum, and now your cross correlation is terribly confused. So how do we deal with this? Under the standard methods frame, there are roughly two ways. One is from your observed spectrum, you can divide out the tellurics, right? You either take an observation or you construct some model so that you think you know what the telluric absorption lines are like. In your observed spectrum, you just divide them out. Or if you're using forward modeling, you can model it, right? Especially if you're doing the blue times orange and then convolved with your spectral graph line spread function fashion for modeling. So how well do we do? Well, I should say that this is the work we're finishing writing up right now, led by me and my undergrad student, Natasha Letou from George Mason University. So this is a one-plot summary of how well we can contain the problem of telluric contamination to our best efforts under the standard frame at the moment, right? This is a plot of radial velocity error as a function of wavelengths. And again, no photon errors are involved here, just the contribution from tellurics. Those horizontal bars mark different optical or near infrared bands. And let's first focus on the light blue lines. Those are marking how much errors telluric contamination is inducing in radial velocity across different bands, right? If you don't deal with them at all, because in the optical, they're not too bad, below a meter per second also, but in the near infrared, they really blow up. All right, so now let's look at the dark blue line, which is the method where you assume you know the telluric lines perfectly well, and you divide them out from your observed spectrum, and then you perform a CCF, right? Then how well do you do? That's the dark lines. As you can see, the improvement from the light blue line is very often order of magnitude. This is a log plot on the y-axis, by the way. So this improvement is very often order of magnitude or a factor of 2 also. And the orange and green lines are just bearing some more realistic assumptions about our lack of knowledge of the atmosphere. Very often we don't know the telluric absorption lines perfectly well, right? So they do a little bit worse than the dark blue lines. But the takeaway home message is that in the optical region, we can aspire to contain this problem to the order of 10 centimeter per second or even below. And in the near infrared, it's a little bit struggle. This is 1 meter per second, right? But we can aspire to contain this problem on the order of 1 meter per second, definitely below 3 meter per second, maybe even better in 1 meter per second in certain bands for sure. All right, so now it's time for fun fact number 2. We just looked at the plot of telluric contamination's reduced velocity arrow. And I mentioned that when we know the telluric absorption lines perfectly well, we can divide it out in the observed spectrum and then perform CCF. But as you can see in the previous plot, this method does not eliminate the errors completely. You're still left with some residues. Right? Why is that? You already know the telluric absorption lines perfectly. You're dividing them out. So what's wrong? Well, the answer is this very important sentence. Convolution does not distribute over multiplication. What does this mean? All right, let's go back to this picture of how tellurics enter the picture. You have your stellar spectrum, you have your telluric spectrum, you multiply the two to mimic the process of telluric absorption in the atmosphere. You have the multiplied spectrum, and then it goes through your spectrograph and it gets broadened, right? This process is convolution. You convolve this multiplied spectrum by your line spread function, right? So you have to multiply first and then convolve. And when you're trying to divide your telluric spectrum, which is the orange convolved with your line spread function from the observed, it will not give you the blue spectrum, because if you convolve the blue, convolve the orange, then multiply the two, it will not give you the red, right? Convolution does not distribute over multiplication. This is origin of the error. And this error roughly scales with the line depth. So in the near infrared, this is a more severe problem, while in the optical, where you mostly have shallow telluric lines, is much less of an issue. All right, so we talk about how to deal with various contaminations, and we think we have some clues to contain it, at least in the optical, to our desired 10 centimeter per second precision, which is what needed to detect Earth-like planets around sun-like stars. All right, now for stellar variation. The standard methods do not distinguish between Doppler shifts and line deformation-induced Doppler shifts. This is a large limitation of the standard methods I just described, right? You can imagine we are trying to do a CCF or your modeling. The code does not care whether your measured, your best fit Doppler shift is a pure Doppler shift, or maybe it was just because your line has a little bit change in the shape between the two epochs, right? That could effectively cause your code to produce a Doppler shift. And traditionally, the way we deal with it is sort of post-mortem. That is, we measure a Doppler shift Z. We know it contains the component of stellar variation, say caused by line deformation, change in the shape, line shapes, and also planet. Now we try to use, say, activity indicators like the line bisector and full width half max I mentioned before when I talked about CCF. And we try to determine what is the thick Doppler shift caused by the star itself and just subtract it out. As you can imagine, this is sort of less than ideal, right? And that's this is behind, this is sort of the motivation behind a lot of the currently newly developed or currently under development new pipelines. And for more on stellar variation, please look forward to talks by Heather Segla, Annelies Mortier, and Jennifer Burt. So this brings us to the final topic of non-standard methods for measuring UV velocities. There are roughly 3 families of new methods being presented or being developed at the moment. This is just my sort of mental characterization for those new methods. The first is what I like to call the grand solution. So this is not a term coined by me. This was invented by Jeff Valenti, who's an astronomer at Space Telescope Science Institute. And Jeff Valenti and BJ Fulton got the grand solution to work on high-res data first, being the first in the industry. So the way grand solution works is like this. You have a series of spectra, and you don't know the stellar template, right? This is not something that is you know a priori. But you can assume that the underlying spectrum of the star is something that doesn't change, right? So in your series of observed spectra, the only thing that changes is the Doppler shift. So you can simultaneously fit all of your observed spectra in this time series and solve for a common stellar template, solve for the underlying stellar spectrum, while producing the radial velocities for the spectrum at each epoch, right? This is why it's called the grand solution, because you're doing a global optimization, right? This method is also implemented by Peter Gao and Peter Plavchang and team for seashell, and later on its upgraded version iShell on IRTF. This is measuring velocity in the K-band. And it's very challenging because there are a lot of uncertainties in the near infrared that are unique, that don't exist in the optical region. And they implemented the grand solution method and successfully got to 3 meters per second, roughly, which is pretty impressive. And another code that sort of follows this grand solution philosophy is this wonderful code called Wobbly, like Michael Bublé, by Megan Bedell, published last year. So the previous mentioned work deal with absorption cell calibrated data mostly, but Megan's code deals with stabilized spectrograph data. And one of the motivation behind Wobbly is to deal with tellurics, which is blended lines, just like absorption cell lines, right? I'll talk a little bit about Wobbly next. And the second family is using Gaussian process. As you know, this is a hammer, very powerful hammer that we could apply on many methods. So Gaussian process is very often used for modeling RV time series, but in this case, this is used to measuring spectra, right? The first one that was published is called PSOAP, written by Ian Chakala, but this is not exactly employed for high precision radial velocity, but more for spectroscopic binary stars. And then earlier this year, the brilliant Vinesh Rajpal published a code using Gaussian process to model observed spectrum and measure radial velocities based on the best Gaussian process regression fit. I'll also briefly touch on this. And there are also other families of methods. For example, using machine learning, taking advantage of the fact that Doppler shift is a achromatic shift or stretch in the spectrum. And you can use something like principal component analysis to tease out just this pure shift component vs the other, say, color or line dependent or depth dependent fake Doppler shift, right? And there are also groups working on using other unsupervised or supervised machine learning methods, such as neural network, to get radial velocities out. And also other statistical or numerical methods are being developed to take advantage of this fact that Doppler shifts, pure Doppler shifts caused by planets are achromatic, right? You can just tease out that component in your data. All right, so very briefly, I want to introduce Wobble and also Rajpal's Gaussian process pipeline. So Wobble is really cool because no prior knowledge is required on either the stellar spectrum or the telluric, all the telluric spectrum. No, not at all. So it grabs your time series of observed stellar spectra, and it solves globally for a time invariant stellar spectrum, a time variant telluric spectrum. So the telluric lines are allowed to vary in depth, but not in wavelength space, unlike the stellar spectrum. And it solves all the velocities at the same time. So as you can imagine, this is a gigantic optimization problem, which they employ the machinery in the Google's TensorFlow package, which is the driver behind Google's neural network. It actually runs really fast and it's fairly easy to implement. This is really cool. This is the one example feeding the H alpha line. The red line is the best fit stellar spectrum, and the blue line is the telluric spectrum it was able to tease out. It's really impressive. And the second is Manish Rajpal's Gaussian process method. So it does a pairwise extraction of radial velocities with Gaussian regression, in the sense that it grabs a pair of spectral observations, and within those pairs, it measures RVs relatively in between each pair of spectral orders. It solves for the stellar spectrum using a Gaussian process, describing the spectrum naturally, because you can imagine spectral lines are just basically points that are highly correlated in the wavelength space. This is one example GP feed from his paper. And then how does it deal with contamination? Well, after it determines the radial velocities, it goes back to see which orders perform badly and sort of exclude those contamination caused by either telluric lines or stellar variation, and then just kick them out from this suite of radial velocity from those pairwise measurements, and then rejecting those orders. And indeed, they see an improvement in comparison to other methods. And I just want to highlight really quickly this very cool feature. Just one small advantage of using Gaussian process to describe your stellar spectrum is that now your CCF is no longer discrete, right? Before we're using a discrete template on a discrete observed spectrum, and this is your CCF. The dashed line is the correct answer in this simulated result from simulated data set. Now, once you use a continuous function to describe it, and now you have a continuous CCF, which is really cool. All right, so we roughly covered stellar variation. We think we may have some hope to contain this problem using pipelines being developed. But this is yet to see. And I just want to mention that for all of those new pipelines, the examples very often were given based on HARPS data, and the results presented in those papers do not see a significant improvement on radial velocity precision. This is because the standard methods have more or less reached the photon limited precision on the previous generation instruments. So to see a true improvement in dealing with spectral contamination and stellar variation, we need to employ those new methods on next generation spectrograph data, which are mostly being taken at the moment and being analyzed. So there is a lot to look forward to in the very near future on those developments on non-standard methods in RVs. With that, that's all. And please feel free to contact me if you have any questions. Thank you very much.